Given an explanationist framework of probability, this will inevitably affect how we assess the simplicity of theism. In a previous video, I did argue that theism is the more simpler hypothesis if we compare the fundamental postulates of each theory. However, I believe that I made a few errors and wish to correct them here. The first error is in my assessment of the criteria of background knowledge, which I didn't think was relevant. As an explanationist, I now think it is relevant. Another thing was about my assessment of Draper's use of modesty and coherence and my judgment that they are equal. I now think that naturalism, as Draper defines it, actually is more modest than theism, and therefore naturalism is simpler if we compare the overall worldviews. This conclusion is further supported when we consider Graham Oppy's use of the criteria of simplicity. Oppy thinks that our worldview should be treated as your theory. We start off with all your beliefs about the world and then do our theory building. So a worldview, for example, that has less ontological, ideological, and theoretical commitments is better than a worldview that has more. In other words, the worldview which has less beliefs part of it is the worldview that is simpler. I will explore more of Oppy's methodology later, but in regards to simplicity, a worldview with overall less commitments is the simpler one. What is interesting here is that both Oppy and Draper actually get their similar ideas of simplicity from Darren Bradley. This probability distribution assigns higher probabilities to state descriptions that postulate uniformity with respect to metaphysically fundamental properties. Bradley sees uniformity across fundamental properties as a kind of simplicity, writing that his preferred probability distribution assigns higher priors to possibilities which can be syntactically simply expressed using perfectly natural, i.e. metaphysically fundamental properties. I will address why this is important later, but here I will be using a more formal definition of simplicity. In algorithmic probability theory, state descriptions are possibly infinite binary strings of zeros and ones. The distinctive feature of this inductive logic is that it assigns higher probabilities to strings that are more compressible, i.e. can be described more concisely. The notion of how concisely a string can be described is formalized in terms of its Kolmogorov complexity, which is measured by the length of input to a universal Turing machine required to output that string. The precise mathematical details are not important here. But here the feature is that state descriptions with lower Kolmogorov complexity are assigned higher probability. Solomonoff saw this as formalizing Occam's razor. A recent textbook on Kolmogorov complexity echoes this. This gives an objective and absolute definition of simplicity as a low Kolmogorov complexity. Consequently, one obtains an objective and absolute version of the classic maxim of William of Ockham. So on this view, state descriptions with lower Kolmogorov complexity are thereby more probable. However, this definition of simplicity, while valid, I would argue, doesn't actually make a theory more probable under an explanationism framework. For instance, we frequently learn by induction. We reason from observed data being one way to unobserved data being a similar way. It is tempting to try to vindicate this practice by adopting a probability distribution that favors state descriptions that are simpler in some sense, state descriptions that are more uniform and more concise with respect to the extrapolated property. But there are cases where this does not work. Two examples are given by Nevin Klimamhaga. First example, a coin has just been produced that will be tossed twice and then destroyed. Our individuals are the coin C and tosses 1 and 2, and our properties are H and F for heads and fair. The property of landing heads only applies to tosses, and the property of being fair only to the coin, other applications being category mistakes. We thus have 8 state descriptions where not H is equivalent to tails. FC and H1 and H2, FC and H1 and not H2, FC and not H1 and H2, FC and not H1 and not H2, not FC and H1 and H2, not FC and H1 and not H2, not FC and not H1 and H2, not FC and not H1 and not H2. What probabilities should these be assigned? The first 4 should all be assigned equal probability. In all of them, the coin is fair, and so not more likely to land heads or tails. But on plausible explications of simplicity, the first and fourth state descriptions are simpler than the second and third. For example, the former make the world more uniform, assigning the same property, landing heads or landing tails, to the 2 tosses of the coin, while the latter assign different properties to the 2 tosses. This means that if we assign higher probabilities to uniform state descriptions, we will wrongly assign a higher probability to the first and fourth state descriptions than the second and third. It means that Carnap's inductive logic vindicates too much induction where it shouldn't be. Now what if we follow Bradley and adopt an inductive prior that only favors uniformity over fundamental properties? The property of landing heads is presumably not metaphysically fundamental, and one might doubt whether coin tosses are even individuals. However, restricting our favoring of uniformity to the metaphysically fundamental does not avoid all counterexamples. Consider charge. The world contains exactly two fundamental particles, A and B, and one property, charge C. A random process determines whether each particle is C, where R is the information that the process that determines whether each particle is C is random. This gives us four state descriptions: R and K and CB, R and not K and CB, R and K and not CB, R and not K and not CB, not R and K and CB, not R and not K and CB, not R and K and not CB, not R and not K and not CB. What probabilities should these be assigned? Charge is structurally identical to coin, but charged particles are clearly a kind of thing, and C is, we can stipulate, metaphysically fundamental. Charge is thus a counterexample even to Bradley's restricted principle, on which state descriptions that make metaphysically fundamental properties more uniform are more probable. R and CA and CB assigns greater fundamental uniformity to the world than does R and not K and CB. So this principle implies that R and K and CB is more probable than R and not K and CB. But this is the wrong result, because R includes the information that whether A is C is randomly determined, implying that R and not K and CB and R and K and CB are equally likely. We might instead try to assign probabilities based on some other formal property of state descriptions, but this is unlikely to avoid the above counterexamples. For example, Draper proposes replacing simplicity as a basic criterion of probability with coherence. But Draper's explication of coherence is one we have already considered for simplicity, namely uniformity. Quote, hypotheses that attribute real uniformity to the world are to that extent more coherent and thus more probable intrinsically than hypotheses that attribute real variety, either at a time or over time. So although Draper sees his criterion as a rival to, rather than an explication of simplicity, functionally, this account ends up with similar consequences to Carnap's and Bradley's. For example, FC and H1 and H2 is more uniform, and so on Draper's account more probable, than FC and H1 and not H2. This is why simpler worlds are not always more probable and why we need an explanationist framework. On the explanationist model, inductive inference proceeds via explanatory inference. Abduction precedes induction. We should not conclude that what we have not observed will be like what we have observed because this is the simplest hypothesis. We should do so because, usually, this expectation is the one best supported by the most probable, higher-order explanatory theories about the underlying workings of nature. So on explanationism, whether and how we should learn by induction in a given case depends on the content of the domain in question, and our background knowledge K about that domain. So given the examples above the impact that A1, the proposition that our coin lands heads the first time it is tossed, has on A2, the proposition that our coin lands heads the second time it is tossed, is mediated by its impact on higher-order hypotheses about the bias of the coin. The value of P, a two-conditional on A1 and K, is determined by the probabilities of a two given different hypotheses about the bias of the coin, and how these are affected by the coin landing heads the first time. Since, we stipulated, K entails that the coin is fair, our probability distribution over different bias hypotheses is not impacted by H1. Hence, no inductive learning occurs. If K did not tell us this, then learning that the coin came up heads the first time would change the probabilities of different hypotheses about coin bias, raising the probability that it is biased towards heads. By doing so, it would raise the probability that the coin comes up heads the second time. So on explanationism, explanation is prior to extrapolation. Systems of probability that begin by assigning probabilities to state descriptions without taking into account higher-order theories faces a dilemma. Either they will keep us from ever learning by induction by assigning equal probabilities to all state descriptions, or they will favor some state descriptions over others on the basis of simplicity. But in doing so, they will be forced to learn by induction too often, even in places where it should not. So on explanationism, the simplicity of a hypothesis is not about its overall claims in regards to what it requires to be true. Draper's use of simplicity in terms of modesty and coherence assumes the orthodox view, and so the more modest and coherent a theory is, the more simple it is, hence its prior is higher. But that is judging the prior probability of a hypothesis on the unconditional probabilities of overall worldview, judging it based on the number of claims it makes. On explanationism, the simplest hypothesis, the one with the higher prior, is in terms of the simplicities of atomic hypotheses on the same level of explanation, and not the simplicities of overall worldviews. Thus, the prior probability of a hypothesis is a function of how simple are the higher order hypotheses which it contains, and how well they are able to explain all the other propositions which the lower order hypothesis contains. So just because the conjunction of the higher and lower order hypotheses is less modest in its overall state descriptions or overall worldview, that doesn't mean it is less probable. Simplicity, then, may play a role in helping determine the values of probabilities. However, simplicity as defined formally as lower Kolmogorov complexity does not directly determine the probabilities of different state descriptions. Simpler worldviews are not always more probable. The world of probability and the probability of worlds is more complicated than that. I will focus more on Oppie's use of worldview comparison later, since there are a lot of implications that affect how he does comparisons of worldviews, but we can at least know these things to be true. 1. Simpler worldviews are not going to be the most probable on their own, so simplicity needs to be more restricted if we want to generate a higher probability. Regardless if it's intrinsic probability or prior probability, the same rule applies. 2. Draper's use of modesty and coherence faced the same problems as Carnap's and Bradley's induction. Thus, his argument of the intrinsic probability of naturalism being higher than theism do not work under explanationism 3. Oppie's use of comparing the fundamental postulates of a worldview faces problems if not combined with an explanationist notion of simplicity. More on this later. 4. We need to restrict simplicity to explanatory simplicity to generate a higher intrinsic probability. So, on explanationism, the intrinsic probability of a hypothesis is a function of how simple are the highest level hypotheses which it contains, and how well they are able to explain all the other propositions which the world contains, rather than the totality of the world view. Now, because simplicity on its own doesn't increase a hypothesis' intrinsic probability, then we can only argue that theism is more intrinsically probable if theism can serve as an explanation of phenomena. Since simplicity must be filtered through some kind of level of explanation, then we need to first establish how theism works as an explanatory hypothesis before we can proceed to argue that it actually does have a higher intrinsic probability. For that reason, I will argue in upcoming videos that theism is a good explanation of the world.